Okay, thank you. So I'm going to continue where we started yesterday, but on a slightly different track. So yesterday, actually, I'm going to start by reviewing what we did yesterday, and then I'll tell you what we do today. So yesterday, I tried to explain the general philosophy of the SYZ construction of mirrors to a log Calabi-Yau. The idea is to start from a Lagrangian torus fibration on the complement of some anticanonical divisor, to first build an uncorrected mirror, which is basically some space of Lagrangian fibers of my torus fibration, together with unitary rank 1 local systems on them. And we've seen that this is an analytic space locally modeled on pieces of the algebraic torus over the normative field. And then we discussed how the presence of holomorphic disks in X with boundary on those fibers modifies the answer. In particular, Maslov index 0 disks are responsible for wall crossing jumps in the mirror. So we get some wall crossing analytic changes of coordinates across each codimension 1 wall where there are Maslov 0 disks. And Maslov 2 disks also, if we count them, equate the mirror with a function called the superpotential, which is an analytic function locally. And the wall crossing jumps in that superpotential get cured by the wall crossing transformations. So we went through all that. Let me just remind you the kind of coordinates we like to put on a mirror space are these kinds of quantities, which are the Novikov variable t raised to the power of the symplectic area of some relative homologic class of degree 2 times the holonomy of a local system along the boundary loop on my Lagrangian. And so, for example, the weights in Floer theory of holomorphic disks are monomials in these variables. And this is why Floer theory has a local analytic dependence on the coordinates we use on this mirror space. Then we discussed the M0 obstruction for a single Lagrangian and how disks of different Maslov indices contribute terms of different degrees in this story. And the belief that usually Maslov index 0 disks will happen along codimension 1 walls in the base, and Maslov index 2 disks will exist everywhere but can be just counted by a regular function in the mirror. And we walked through an example that was the blowup of a toric fourfold to convince you that we could actually end up with situations where the wall crossing transformations are actually inconsistent in the sense that when you look at the various charts in the mirror, in this case corresponding to product tori of different radius, there are jumps as the radius passes through one of the blowups we did, and those jumps are cured by coordinate changes in the mirror under which the expressions match, but the whole picture is inconsistent. The reason for the inconsistency in this example was the presence of a Maslov -2 disk at a specific place in the middle of the diagram where the walls intersect. And that Maslov -2 disk, of course, because Maslov index is twice the intersection number with the boundary divisor, that was not just a genuine disk, because that has positivity of intersection with the divisor D. Rather, it was a disk of Maslov index 2 together with a sphere of negative germ number contained in the divisor. And we ended with a discussion of how we can still think of this inconsistent mirror as a deformed Landau-Ginzburg model, in the sense that mod some of the terms, mod terms that had these coefficients q prime, q double prime, which were some Floer weights of certain curves, we had something that was an honest Landau-Ginzburg model. And the further terms involving this quantity which basically comes from the Maslow index -2 disk and everything that is formed by attaching it to something else, essentially, can be viewed to altogether build a cocycle in the Hochschild cochain complex of matrix factorizations of the superpotential ignoring this. Or more precisely, you can think of it as a collection of cohomology classes in polyvector fields. There is a check to cochain with using the second exterior power of a tangent coming from the Maslow -2 disk in the middle of the diagram. And there were also some cocycles of degree 1 and 0 coming from Maslow 0 and Maslow 2 disks that were generated by attaching this special disk to other disks. All right, so today I want to restart kind of, forget about the example, I mean, not completely, but mostly, and start instead like building some kind of possible approach to the theory of what just happened and how do we incorporate not just Maslow index 2 and 0 disks into the story of building a mirror, but also negative Maslow index disks. And I don't know, I'm calling this maybe a bit pompously a family Fleur approach, but well, it's kind of half-baked. I mean, I'm kind of still approaching from far away, and it's not yet really honestly family Fleur. Yes. So returning to positive Maslow index. So remember the theme there is disks of Maslow index mu. Let's go back a bit somewhere where this was. The first thing I pointed out is that if I just look at the moduli space of disks of given Maslow index with boundary on one Lagrangian, this has expected dimension n-2 plus Maslow index. And so if I look at M0, which is just disks with no inputs and one output, this contributes something of degree 2, cohomological degree 2 minus Maslow. If Maslow index is bigger than 2, this vanishes for degree reasons. Now, of course, higher Maslow disks can still enter in other Fleur operations. If you start putting incidence constraints, inputs on your holomorphic disks to cut down the dimension, then it might still come up. But this and I guess this tells me at least as far as the 0 input part of the Hochschild complex is concerned, disks of Maslow index more than 2 don't contribute. Anyway, I'm interested in going towards higher Hochschild degrees rather than lower ones. I guess, yeah. And, so similarly here at the level of talking about Hochschild cohomology, this degree should be 2 minus the Maslow index, basically for each piece that we see. And so, well, except this is not quite graded. I mean, sorry, this is for the wrong grading. This is, for this grading, it's degree 2 minus mu. All right. Oh, no, it's the same grading. Never mind. Let's see. Okay, so let's restart. Okay, this is not how I wanted this set up. Just a second. Okay, that's going to be better. All right. So we wanted to restart from a Lagrangian torus vibration on the complement of divisor D and the uncorrected mirror. And now we want to think about how we might have, what is a good mechanism for encoding all the wall structures or counts of disks, not just for a single fiber the way M0 does, but for in fact a whole family of disks. Sorry, for a whole family of fibers of pi. And again, just the smooth fibers of pi. So first thing I need to say is what kinds of coefficients will we do Fleur theory in? And the answer is, for a single Lagrangian, I was doing Fleur theory with coefficients in the Novikov field, and I had elements of that Novikov field that were the weights of certain holomorphic disks. Now I should imagine instead that these weights, Z beta, which are the weights of holomorphic disks, they are going to want to be sections of a sheaf of analytic functions on the mirror, in fact. And so what I can do is I can look at the sheaf of functions on this uncorrected mirror and push it forward by the dual projection. I mean, this pi check is basically the valuation locally. I have pieces of you have pieces of k star to the n, and I have a valuation map to a piece of r to the n, which are like affine coordinates on B. And so this push forward of analytic functions, well, it's basically going to be just defining a sheaf on B0 whose, locally is built like some completions of Laurent polynomials in these variables z1, zn, in which the weights are monomials. Okay, so the observation is we start with a grouping of the homology of a fiber, and that is where a single weight of a disk class lives. Z beta is a monomial in z1, zn. And then, of course, we need to have infinite sums which are adequately convergent, and so we take some completion of that. And we can view that as a sheaf on the base. So now we want to do simultaneously Lagrangian Floer theory for disks in X with boundary in any fiber in the family of fibers of pi. Again, just the smooth ones, with weights that will now be in this sheaf ON. That's a stupid name, but you leave me alone with like terminology problem and find a stupid name. That's whatever. Okay. And so the claim is, out of this Lagrangian Floer theory, we should be able to build curved infinity operations, not just on the Floer complex of a single Lagrangian at once, but actually on basically some family Floer complex, which I will write as some flavor of cochains on B with coefficients in cochains on the fiber with coefficients in ON. And of course, by some kind of Kuhn thing, you could also just say this is some flavor of cochains on X with coefficients in pullback of ON, something like that. Now, what do I mean by cochains? Well, I'll try to answer some of that later. For now, let's just pretend that they're your favorite kind of cochains, whatever that might be. For example, the naive description of M0 is we look at moduli spaces of disks with one output marked point and evaluation maps at that marked point, and that, of course, will land into usual chains on your Lagrangian. And as you let your Lagrangian move, you will have maybe chains on the base with coefficients in chains on the Lagrangian. So if I want to think of them dually as cochains, there's models like singular de Rham chains or things like that that look like that. The big drawback they have is that to be able to actually define a fundamental class fundamental chain for the compactified moduli space of disks, one needs technology that I'm not somehow comfortable with. I mean, I believe it's great, and if I'm not trying to cast any doubt on it. I'm just saying personally, I'm not able to work with it and actually get at a number for you. And so, you could use some kind of virtual fundamental cycles, chains, some kind of Koranishi structures, or I will offer to you a more theoretic model in the second part of this talk. For now, let's just suspend this belief. This is some kind of cochains on B0 with coefficients in cochains in the fiber. And just for dimensional reasons, this is going to be in degree 2 minus the mass of index global. Okay, so you should imagine, for example, mass of index 2 disks. You can count them through any point on any fiber. And so this should be something of cohomological degree 0, because it's a 0, it's codimension 0 thing. And instead, disks of lower mass of index come in some codimension, and I expect to get at the end a cochain of that cohomological degree. So a small comment here about what is this, beta? What is beta the class in? So beta, of course, is a class relative, it's a class in pi2 of x relative to whichever fiber the disk lives on. And you might be uncomfortable with that until you remember, or maybe it's implicit in the definition of this sheaf ON, that these abelian groups where the homological classes live, they form a local system of abelian groups over the base B0. So you can transport them along your favorite paths. And yes, if you have monodromy, you have monodromy. But you can define locally Z to the beta in this way. Okay. So what do we expect from experimental evidence rather than, I don't have really a proof of that. So first thing I expect is that in good situations, and maybe I would take that as a definition of the family being family weakly unobstructed, the M0 that I can define in this way by counting all disks with boundaries on all the fibers will actually split, according to mass of index, into terms that have the same cohomological degree in the base and in the fiber. So mass of index 2 disk counts, I would like them to be codimension 0 in the base, 0 in the fiber, mass of 0 codimension 1 in each, and so on. And I would hope also that fiber-wise, I can assume that these are kind of fiber-wise cycles. What that means, of course, depends a lot on what kind of co-chain model you take. If you pass to some minimal model for each Lagrangian, then it's a given. But and again, the guess is that in a tropical limit, holomorphic disks of some given mass of index will want to live along complex cycles of a given codimension. And that's why tropically, they want to live in the same codimension in the base and fiber. Yes. The definition of ON, yes. So ON is the thing in which coefficients live for my universal Floer theory. So, point-wise, Z beta, the weight of a Floer disk, is going to be some monomial in formal variables that correspond to the, local variables really that correspond to the basis of the first homology that I take. Right, remember, if you want this ZIs is going to be, locally something like T to the area of some cycle gamma I times the holonomy of a connection along some loop gamma I for a basis of homology. Okay, so this is, the weight of one disk in a given class always looks locally like a monomial in certain local coordinates. And then I want to take, over a given domain in B0, I want to take the completion, which corresponds to series formed out of these Z betas, which adequately converge at every point of my open set. Yes, kind of. So basically, it's it's kind of the assertion that the places where the walls of disks of certain mass of index live are actually going to be Hodge classes. And of course, this is more like in the tropical Hodge sense. Again, we're supposed to try to do this near tropical limit. So. Okay. And this happens in practice. It's not like I have a proof for that. I don't really know, because the starting point of that would be the claim that the unions of all the disks that you ever see will want to be some complex cycles, and I'm not sure that I know how to justify that rigorously. Okay. Now, the other thing, which is also slightly fantasy, is I think this M0 should satisfy a Maror-Cartan or master equation, which roughly looks like delta of M0. So that's like its boundary for some classical boundary operator on these cochains, plus 1/2 of a certain bracket of M0 with itself should be 0. And so this master equation is kind of equivalent to the consistency requirement in general for the wall crossing structures you will get out of this story. And also, you should be aware that, there's already been a history of these equations. That's mostly the work of Fuqua and Iraye. For one Lagrangian, the question is, what is the structural property that M0 satisfies? And the most obvious one from infinity structures is M1 of M0 is 0. It's not this. But what Fuqua and Iraye pointed out is if you enhance Floer theory over a loop space, then there is a loop space valued M0, and that one wants to satisfy the Maror-Cartan equation because of how boundaries of holomorphic disks want to break into pairs of boundary loops of holomorphic disks. Okay. So we'll get back to that at some point. In fact, at the end of the talk, I'm even going to try to kind of sketch a possible proof of the master equation in some half-baked model for doing all this. But anyway, so I'm going to first tell you a bit more about what happens when these expectations are met. And of course, I need to tell you what this mysterious bracket is. Okay. So let's assume that the family M0, counting disks with boundaries on all the fibers, is going to be a sum of things of codimension I in the base, codimension I in the fiber, and they are actually just cycles fiber-wise, so that I can take this changed, cochains in the base to have coefficients in cohomology of the fiber. So alpha I is going to be the ith term in here and records codimension I rows of disks of mass of index 2 minus 2i. So what is the bracket I want to have? So it starts from a bracket on. So remember, this thing is locally a completion of a group ring of H1 of a fiber. So, undoing the completion for a moment, I need to tell you of a bracket on the cohomology of a torus with coefficients in the group ring of its first homology. So this is also, you could say, this is a polynomial algebra, and this is an exterior algebra in the dual variables. Okay. So what I can do is take the operation where, so I take a monomial z to the gamma on this side, times a cohomology class alpha. Sorry, I think my notations are kind of messed up, whatever. And I have another one, z to the gamma prime times alpha prime, and I kind of multiply them. So the normal product would be take z to the gamma plus gamma prime times alpha wedge alpha prime. But instead of doing just that, I am going to do the interior product of gamma into, so the exponent of the monomial for alpha, into the class alpha prime. And then I will skew symmetrize or symmetrize, depends on what you mean by that. Okay. So this is a degree -1 bracket. It has some nice properties. And one way to think about what this is that secretly, this is the Chef-Sullivan string bracket on the homology of a free loop space of a torus. Okay, so the free loop space of a torus has as many components as there are classes in H1. And so you get the group ring part, and each component retracts onto a copy of the torus. That's where you get the exterior algebra from. Yes. This is the same as Gerstenhaber and things and so on. And all of these also come from really a product and a BV operator. And I mean, there's a lot of things there. I kind of, this is not like my natural world to be in. And so I try to kind of educate myself on all those structures, and it seems like there are tons of structures in there. Yes?
Yeah, so secretly use the convention quantization liberated from also complex, yeah. This polyvector fields, and it's very much close trying to this other dots, that fits in this discussion. The convention quantization is something really.
So you're saying there are higher terms. Yes, I'm aware that there are higher terms in this bracket. Yeah. I'm aware that this is beginning of, and for me, I'm just going to say a shifted L infinity structure. But remember, this is on a torus. So I think. Okay, thank you for saying. I wasn't sure. I was going to ask you at the end, and okay. Yeah, I guess so. Yes. Okay. All right. Okay, so anyway, so this weird formula, you can think of it as being, if you're a loop space person, this is the string bracket on loop spaces. The string bracket on the free loop space is basically you have two chains on the free loop space. And you ask, when is the base point of one of my loops going to live on some point of the other one. So in fact, when is it attached here? And if it is, then compose the loops by inserting it into the right place and vice versa. Okay, this is what the string bracket is about. Insert one loop into the other one whenever that's possible and select whichever elements of your chains make that happen. Okay, so now we're going to extend this first by doing completions to infinite sums of such things, which is where we land in this. And then the second thing we do is, now that we have not just the fiber and those monomials, we're going to add also cochains on B0, and so we need to add also the cup product on B0. So, okay, so yes, I mean, people went right ahead into Hochschild things, and we're going to get there at a slower pace on the mirror, because that's where I'm kind of more comfortable with HKR theorems. But yes, you could have already gone Hochschild before that. So how do we pass this to the mirror? I mean, we could say tibialize or whatever. So the observation is H1 of the fiber is the same thing as the tangent space to the base. That's a basic property of Lagrangian torus fibrations, that the normal bundle to a torus is canonically isomorphic to its cotangent, and constant sections of the cotangent on a torus is H1 classes. So what that means now is the cohomology of FB I can think of as an exterior algebra modeled on the tangent of a base B. And through some non-Archimedean lifting process, something, this ends up, these quantities that we are manipulating, which are monomials in the ZI coordinates times wedges of elements of, some basis of H1, we can actually turn them into polyvector fields on the mirror. I wrote isomorphic. I think that's maybe a bit optimistic, so maybe I should kind of retract the isomorphism. Okay. So basically, all I do here is I turn the part that's about the cohomology of the fiber into things that are about the tangent space, and I get polyvector fields. So if I do that, and then I can turn my M0, which was a collection of cochains on B with coefficients in cohomology in the fiber times Laurent polynomials, into something I will call W, sum of terms, which are now cochains on the base B, but I can lift that to cochains on the uncorrected mirror, pull back, with coefficients now in the exterior algebra of a tangent bundle. And so now we find the next incarnation of our bracket, which is that under this map, the bracket I wrote up here turns into this Cartan-Nierenhaus bracket on polyvector fields. So that one, what's that? It's some multilinear extension of things like the Lie derivative by a vector field. And so basically you look at, you have two polyvector fields, and you look at ways of differentiating one along the vectors that make up the other, and you kind of sum and alternate and so on. And it's exactly the same as this construction. It's just a simple calculation. Up to sign, somehow I can't get my sign convention straight at this point. Okay, and so that means if M0 satisfies the master equation, then so does this bolt W that we get on the other side. All right. So what is the geometric content of this? So now we have a sum of terms, which are I cochains on the mirror with coefficients in I polyvector fields. And first observation is that the Markov equation for W is equivalent to saying that a deformation of the usual differential by bracket with W squares to 0. Okay. Again, this is probably kind of trivial for people who have a sufficiently algebraic understanding of things, but coming at this from very down to earth geometry, I kind of, was then, okay, what does this mean in real life? And so you can expand this order by order. The first few equations, it's kind of advantageous to, in particular, look at delta plus the bracket with W1. That's the part of this operator which preserves this degree here. Sorry, doesn't preserve, but it's homogeneous, right? It increases degrees by 1 everywhere. And so with respect to this differential, W0 has to be closed. It's the first equation. That's probably the degree 1 term in this, actually. The degree 2 term in this one says that the square of delta plus bracket with W1 is in fact the bracket with the bracket of W0 and W2, which concretely W0 is a function. This is the interior product of dW0 into the bivector field W2. And then there's more and more. So to square this with the usual viewpoint about what different Maslov index disks do to the mirror, this says, okay, first thing we should do is we should think of W1, which is the one that comes from Maslov index 0 disks, as a deformation of the analytic structure of my space. So what that means depends on what kinds of cochains I have in mind here. If I use check cochains, this will mean really I will deform the gluings between two different charts in my open cover by the vector field, which is the value of W1 in that overlap. If I'm doing Dolbeault cohomology, then I will deform the del bar operator by instead W1, which is now a 0-1 form with coefficients in the holomorphic tangent. Except I'm non-Archimedean, so I should be doing tropical Dolbeault cohomology and so on and so on. Right. Okay. So now with this understood, the first equation says W0 is analytic with respect to the deformed structure. Okay. Superpotential is still an analytic function. But the second equation says the deformation actually fails to be, it's obstructed. And what I get is not quite an analytic space because there's an inconsistency, which is this thing, interior product of dW0 into W2, which is a two-pole chain with coefficients in the tangent. So if I'm in the check world, this is kind of what we saw in the example, the coordinate changes fail to satisfy the co-cycle condition by this amount. If I'm in the Dolbeault setting, this is actually more fun. It says del bar squared is not actually 0. It's actually given by something, well, C2 would now mean 0-2 form with coefficients in the tangent. And that's exactly where the Nirenhaus tensor of an almost complex structure lives. So it says basically we've deformed the analytic structure to a, well, I mean, if I were really complex, I would say an almost complex structure with prescribed failure of integrability. Okay, and in all cases, it's worth noting, because this annoying term involves the interior product in dW0, if you're at a critical point of the superpotential, dW0 vanishes, so this curvature term vanishes, and so that means the critical locus of the superpotential is still an honest analytic space. But of course, the normal data is possibly messed up. And I think that may actually mesh with some old observations of Konstantin about what happens to a Landau-Ginzburg model when you kind of are a bit sloppy or not so sloppy about the normal directions. So of course, here the space becomes more exotic, but I think this has something to do with it. Okay. All right. So this is basically where I wanted to kind of end this part of the story. Yes, possibly, yes. No, I don't know. I don't know what we can actually or cannot do. Actually, this is just like exploring, some land that lays ahead and then kind of trying to find some bearings in there. It's not like I'm making any very precise claims about exactly what happens. I think I'm reasonably comfortable arriving at some check things, and even then, so I'm going to give you a proposal for what to do, and I'm aware that it has some rough edges, which well, I'm not going to show you the rough edges, but I know that some of the things I will say now need to be amended a little bit. Okay. All right, so I wanted to now move on to a little bit about how exactly could one try to set up this family Floer theory if one is not willing to learn about Koranishi structures, or at least one learns and one's not kind of smart enough to figure out how to actually contribute to that story. So instead, well, there's a more theoretic model that's kind of particularly pleasant, I think, and you're going to see it's not just sorry, to backtrack a bit, right? You could probably end up directly in the Dolbeault world by using some version of singular de Rham chains and some process to perturb by kind of smudging everything so that all your evaluation maps become submersive once you factor in some extra perturbation parameters. And so in this sense, you could imagine that you can build a model by instead of having honest walls, everything has been smudged so that it's given by some actual differential form supported on some thickening of the wall. And you might hope to produce directly a Dolbeault model by having these densities of local densities of holomorphic disks really be encoded by differential forms. I don't know how to do that rigorously. There are big problems with setting up consistent perturbations and smudging in a way that's compatible with disk bubbling. So I'm not going to try to do that. But okay, so in a Morse model, you would start from a Morse function, not just now on a single Lagrange. So sorry, for context, what I'm doing is this is kind of related to what's sometimes called the Pearl model for the Floer homology of a single Lagrangian. And then there's an upgrade to that by Charest and Woodward to construct the A infinity operations, again, on a single Lagrangian, but in a way that is amenable to this upgrade here to a family. So, yeah.
Are you imagining somehow you get like this model as basically the transfers?
Yeah, I mean, they can be made transfers by domain-dependent perturbations. Okay,
like you say, why?
Yes, exactly, stabilizing divisors. And I'll tell you a few, I mean, there's two important pitfalls to be aware of, but neither of them is serious. The thing I have not looked at exactly yet in Charest Woodward is how they deal with the pure Morse transversality things. I know they perturb their Morse flow lines. I haven't understood enough yet of how exactly they do that to have confidence in what's not on this slide, but like 2 slides further. Okay, so what's my favorite Morse function now on the total space x0? So my proposal is we start from I wrote triangulation, but really I think some kind of polyhedral decomposition would be just fine of a base B0, and we'll produce a Morse function on B0 adapted to that. So we decompose B0 into pieces, and then you might build a Morse function that has a minimum here, a minimum here, a minimum here, and here it has a saddle, here it has a maximum, and so on. So basically one critical point on each cell of a subdivision of index equal to its dimension, and pick a metric where the descending flows from a given Morse critical point are going to be exactly the closure of, well, exactly that stratum. Okay. And then add on the fibers above those critical points, including them B sigma, a critical point associated to a stratum, add some perfect Morse function on the fiber with 2 to the n critical points corresponding naturally to your favorite basis of the cohomology of vectors. So what that buys you is you can arrange that the Morse complex of this function f looks basically like the check complex of the base with coefficients in the cohomology of the fiber for the open cover of the base by the stars of the vertices. Again, I have not checked what happens in the A infinity operations on Morse theory, but at least the differential looks like that. Okay. So then we're going to define Floer operations on this Morse complex with coefficients in the weights that we like to have by counting. So now what do you mean by ON? At a given critical point corresponding to some cell of a division P, the coefficients will need to be, of course, in the things that are Novikov convergent over the star of itself. And we will count perturbed J-holomorphic treed disks. So things that look like this. This is like part of an M2 operation. You may have inputs that are critical points of F. You have an output always, which is a critical point of F. And you have Morse flow lines of the gradient of F inside the ambient space. So those drift from fiber to fiber. And at some points, you can decide that you will attach a holomorphic disk with boundary on the Lagrangian fiber right where you are at that time. And then you can continue your flow lines. So, okay, so this is a collection of gradient flow lines. Oops. Gradient flow lines of F in the total space and J-holomorphic disks with boundary on a single fiber at a time. But that fiber can be anywhere it wants along the flow lines. So we will count these with weights that are, again, as usual, the weight associated to the class of the disk. But what we have to do is we collect the homologic classes of all the disks we encounter, and we transport them along the flow lines to a relative homologic class at the output. So there's several problems with this. First, most pressing one is how do we achieve transversality? And the basic answer is in terms of transversality for holomorphic disks, there's an approach explained in Charest and Woodward, and before that goes back to Silliback and Monker for closed Gromov-Witten theory. What you need to do is you will add a bunch of interior mark points to your disk just by marking all the intersections with some sufficiently positive divisors disjoint from your Lagrangian. And once you have all these mark points available, label them in a random order. You will average over all possible labelings, and then choose domain-dependent perturbations. And that will allow you to deal with all the multiple covers and so on problems. Problem here, Charest Woodward need a divisor that's disjoint from the Lagrangian. My Lagrangians can move over the whole manifold. I cannot find a divisor that's simultaneously disjoint from all the fibers. So instead, pick a collection of divisors adapted to various subsets, basically neighborhoods of given fibers. And there's already a mechanism for interpolating between collections of extra marked points given by different stabilizing divisors. Use that to vary your perturbation process over the base. And then you need to also perturb Morse flow lines, of course. So the other problem is Novikov convergence, because normally Novikov convergence comes from the fact that the areas of the disks are positive and bigger than something, and Gromov compactness says below a certain level of energy, there's only finitely many possibilities. But now we're cheating because we're picking disks that happen somewhere, and we're flowing their weights with our Morse flow lines to count them as coefficients elsewhere. And so the Novikov valuation of Z beta, for a disk of class beta, is guaranteed to be positive where the disk happened. By the time I get to the end of my Morse tree, it might not be positive anymore. So the solution to prevent that is to ensure that the Morse flow lines stay in sufficiently small domains in the base B. So basically that my subdivision P of the base is sufficiently fine. How fine? Essentially the same radius as for, let's say, the Fukaya track in family Fleur field. Okay, so I kind of, details are not worked out. My student Kelly Hook is possibly thinking about some of this, and hopefully, this will be fleshed out. But I think basically there don't seem to be any blocking issues. Where there is a blocking issue with this at first glance is how are we going to get the master equation out of this? Because, well, okay, so first of all, maybe I should tell you a bit more. What did we get so far? If we count these three disks, so then we'll get, a sum of generators of a Morse complex. So there will be contributions at the different strata of my subdivision P. And this will naturally want to turn into check cochains on the mirror for the subdivision given by the stars of the vertices. So if I look at the coefficient of my M0 that lives at a vertex of P, a zero cell, so minima of the base Morse function, well, the tree part of my Morse flow tree actually has to stay in that fiber, because the only way you can end at a minimum of a Morse function is by being there all along. So this is just counting disks with boundary in that fiber, or possibly treed, but within the fiber. So this is the usual M0 in the Charest-Woodward way for counting disks bounded by that particular fiber. And then for an edge of a subdivision, so if I have two vertices, and I have an edge and I have a saddle point here, then the contribution, the coefficient of M0 at that saddle point will come from gradient flow trees that live over one or the other half of the edge only. And so that means we'll be counting collections of holomorphic disks that happen somewhere along this edge, together with a flow line bringing it to the saddle. So this is not drawn the right way. Anyway, something like that. And so this means really this will be a family count of holomorphic disks encountered along the edge. And similarly over higher dimensional cells, these are family counts of holomorphic disks that happen wherever they want inside that cell of B0, treed over the Morse flow trees of the Morse function we chose. So in some sense, these are like really not just single disks, but path-ordered collections of disks, which is exactly what you need to get actually the some sort of path exponential, path-ordered exponential that will give you the wall crossing corrections. You don't want just to count a single disk, but rather ordered tuples of disks that you encounter that will successively attach to assemble to the wall crossing transformation. So the problem with that is this has no reason to satisfy the master equation. And the problem is the boundary of this modular space contributing to M0 consists of broken things where we have a broken Morse flow line. Disk breaking is not a boundary here, because when a disk bubbles off, then you just insert a Morse flow line and you continue. That's the whole point of the Perley model. But so this writes, M1 of M0 is 0, and instead we'd like something that looks more like a, instead of having the output of one becoming the input of the other, we'd like to actually pair the outputs by some brackets. So now here we get to something that's a bit more of a fantasy, something I like to call spliced treed disks. And what we'll do is we'll continue, already treed disks continue past the boundary of the usual modular space of disks by saying if your disk breaks into a couple of disks, add Morse flow lines between them. I want to go past the point where Morse flow lines break. How can I do that? So I will allow broken edges, broken Morse flow lines, to start drifting into the structure and splice onto edges where they would not normally belong. What do I mean by that? So a spliced treed disk will look like something like this. I have disks and Morse flow lines, but I have special Morse flow lines that I call splicing edges, which attach to some other edges in a way that's not the usual one. Normally, when two Morse flow line things attach, what you want to do is just make the endpoints of those flow lines be equal to each other. Instead, for a splicing edge, so each edge in this story knows all the disks that live below it. There's some total homology class data, and I can carry that information along me, and I call that the weight of the edge, maybe. And then the condition for a splicing is going to be that the red gradient flow line lands not at a point on the flow line, but rather at a point on some loop through the point at that flow line. So what's happening here is instead of, so through each point, here we have a point X on that flow line, I will pick what I call a standard loop in that fiber, that Lagrangian, based at X, that's more convenient, and representing the homology class, the same homology class as the total boundary of all these disks. So essentially, if you want to know what could have happened before, is there used to be a disk here, and it attached to somewhere on that tree of disks. And so the incidence condition was that my Morse flow line had to end up somewhere on the boundary of one of those disks or the connecting edges. And now I'm going to take that whole loop and let it drift up along this gradient flow line of F and push it to the other fibers further to the output. So the claim in progress is that if you redefine M0 as a count of these spliced tree disks, then it will satisfy an L-infinity master equation. So I can't give you a proof because that's not done. I mean, there's lots of things to be done even to finish the definition of spliced tree disks that will hopefully be Kelly's thesis someday. But just to give you a picture of what the ends of a moduli space of spliced tree disks look like and why you might get a master equation out of this. So imagine that you started from some tree disks, and maybe first thing that might happen is that, okay, there's the usual transitions. Disks kind of, break off, and more Morse flow lines appear. And then, as you keep going, some Morse flow line gets longer and longer, and eventually you have a broken Morse flow line. So that's where the usual moduli space would stop. Past that, I'm going to turn this edge here into a spliced edge, which will now attach to other places along this flow line that comes out of the disk. And now again, the incidence condition means I must actually land not on the flow line itself, but on some loop that is flowing along, starting with the boundary of a disk in class beta 2, and becoming quickly a standard loop of some kind through those points in those fibers. And then, okay, if it keeps going, well, eventually that splicing edge might go all the way to the top of that flow line. So what happens next? Well, what happens next is I'm going to have something where possibly my splicing edge coming from the bottom is going already now to the top of that edge. It's arriving here. But there's other configurations that get into here that are from when I had a disk in the class beta 3 that was attaching directly to that one, beta 1, and that broke, and we start to drift a spliced edge. And so this continues, those two configurations together merge and become spliced configurations where instead this subtree attaches onto this outgoing edge here along a loop that now represents the total boundary of both beta 1 and beta 2 together. And then it keeps drifting up. How far up? Well, until infinity and beyond. Namely, what will happen at some point is that the edge, the output edge of the main tree will break through a Morse critical point. Whoops, that is not at all where I want it to be. That is not good. Just a moment. Okay, better. So now our splicing happens actually infinitely far above the output of the other tree. And so what we have is a completely Morse theoretic structure here at the top, on top of two tree disks. And this is exactly where we are happy to end. And this is a bracket in the sense that, well, this is really not a bracket. This is the operation whose skew symmetrization is the bracket. This operation of one gradient flow line attaches on a loop spread from somewhere on the upward gradient flow line from another critical point. It's the cup product between X, say one of them, and the interior product of this boundary of beta into the other one, Y. Sorry, I got it wrong, actually. The product should be on that side. Anyway, and the point is it's exactly the operation whose skew symmetrization is the bracket. So I believe that this can be fleshed out, then one has potentially a model for getting the master equation. So the next question would be, can we actually go all family Fleur with this? And this slide is kind of half-baked, so good thing because I'm basically out of time. I'm going to show you some stuff. I don't have too much faith that this is actually correct. So if you wanted to do family Floer theory, as in Abu Zaid's papers and then sequels by Heng Yuan, and then you would try to build, out of Lagrangians in X. For simplicity, let's just take sections for now, so that's not very realistic. You can build a sheaf or something that lives over the mirror by taking the Floer complexes of the fibers at all of our cells of the subdivision with L. And then, okay, so you need to equip this with a certain structure. There's going to be some differentials in this. There's partly the Floer differentials, but there's also differentials that correspond basically to check differentials, to kind of assert the property that this is going to be some kind of deformed sheaf over this deformed analytic space. And now the way that you test what you get in there is you might take a morphism in the scale category, so an element of the Floer complex of two Lagrangians, and try to transfer that to a morphism between these spaces. And what you would do is basically this comes from a count of holomorphic triangles, classically, with boundary on L0, L, and a fiber. And now what you want to add to that is a 3D disk part of the story. And likewise for higher terms of your functor with several inputs. And so what we would like to get is some property that says basically that the deformed check differential, accounting for all the corrections, applied to F1 of S. I mean, basically you want this functor to be kind of, in particular, the linear term should be a chain map between the Floer differential on my Lagrangian sections and this deformed check differential we're building on the mirror. And so I think if we introduce splicings, then we may actually get there, because basically, right now, this normally would have boundaries theta where a Morse flow line breaks. And instead, splicing will let you push past that into something that combines by some kind of bracket the output of M0, the disk part. And actually, sorry, there's also still disks here, but M0 with whatever you had defined. Okay, this is all extremely speculative, and I'm not sure if I really believe that I know how to do what's on this slide. But okay, time's up, and I'm done. Thank you.